Okay, so corrosion is a destructive and unintentional attack on a metal. So how does corrosion occur? The problem is very significant in terms of economics because it is approximated that 5% of an industrialized nation's income is spent on corrosion protection and maintenance or replacement of products lost and contaminated as a result of corrosion reactions. And the consequences of corrosion are all too common. You guys can see all around you rusting of automotive body panels, radiator, exhaust components. Sometimes corrosion process is used as an advantage, where if you want to do corrosion, like selective corrosion of certain regions in your part as means of manufacturing. So in this chapter we're gonna see how does corrosion happens, which metals are most likely to corrode, what environmental parameters affect corrosion rate, how do we prevent and control corrosion. We all know that materials will have experience interaction with a large number of diverse environments like salty water, atmosphere. As a result of this interaction with the environment, it can impair the material's properties, physical properties, appearance, mechanical properties due to the corrosion that is taking place. There is also one important distinction you guys need to understand. When we say corrosion, actually we are talking about material loss by dissolution. So your environment, think about like eating up your metal and it's dissolving and disappearing into the environment. But there is another form of degradation that is the formation of a non-metallic scale or film. We call it oxidation, like formation of an aluminum oxide on top of aluminum. So this is also a form of degradation, deterioration of the materials. So corrosion and oxidation, these are actually two different things. And when we say corrosion, we are talking usually about metallic materials, right? Because ceramics and polymers, they have different forms of degradation, not like metals. So, for example, for polymers, when we say degradation of polymers, it is like more likely to they are exposed to UV lights, sunlights that will degrade their properties. Or for ceramic, deteriorations can happen at elevated temperatures or extreme environments. So deterioration mechanisms of each type of material will be different. So how does corrosion takes place? Okay, how does it happen? This is an electrochemical mechanism. So the corroding metal will have both anodic and cathodic areas. So there has to be an oxidation reaction and reduction reaction. So we are seeing pink color, zinc, which is placed in an acid solution. Acid solution is a corroding environment, and it has excess hydrogen ion. You are seeing H plus proton, or we can say a positive hydrogen ion. Okay, so the acid solution have that. So when it comes in contact with zinc, So certain parts of the zinc can act like what can happen in certain parts of zinc, for example. Zinc can give electrons to the environment because the the positive hydrogen ion will want to get the electron from the zinc, so that it will reduce to hydrogen gas. So that is the reduction reaction. The positive hydrogen ion taking electrons from zinc and turning into a hydrogen gas. So this was dissolved in the acid, right? But this is becoming a gas. So of course, to be able to this reaction to happen, there has to be electrons supplied to the positive hydrogen ion, and this comes from the zinc. But when zinc releases its electron, it forms an ion. It becomes zinc 2 plus, and this will dissolve into the solution, as you see. Okay, zinc becoming an ion and dissolving into the solution. But when it's doing that, it is losing its electron to the hydrogen, and from one region of the same material, these hydrogens will come, get that electrons, and then form the hydrogen gas into the environment, release it into the environment. So as you can see, metal atoms, when they lose or give up their electrons, we call this an oxidation reaction. That is what happening for the zinc. And the zinc becomes a positively charged ion. And the site at which oxidation takes place is called anode. Oxidation takes place there. Okay, and when the electrons generated from the metal is transferred to another species in terms of positively charged hydrogen ions, then we call this reduction reaction, right? And this reduction reaction happens at the cathode. We call the region where this happens cathode. So in this case, the hydrogen ion reduced from an ionic state to a neutral state. Besides the hydrogen ions being interested in the electrons of the zinc, there are other reactions that can take place, like the oxygen can grab the electrons from the zinc. So it is not that only hydrogen ions can get it. The oxygen dissolved in the solution, it can get electrons from the zinc combined with water or combined with hydrogen ions, depending on if it's an acidic or neutral solution. It can also react, the oxygen can also react and get the electrons from the zinc, forming either water or hydroxide ion, as you are seeing. Now, there are key things to understand, okay? So for corrosion to happen this way, as you can see, the zinc is dissolving into the environment, giving its electrons to dissolved oxygen gas, or giving its electrons to hydrogen ions. It's dissolving into the environment, and we can say then the zinc is corroding in an acid solution. We are losing zinc. So for this to happen, there are requirements, okay? First, there has to be anodes and cathodes present. Either it can be two different materials, it can be two different materials attached to each other, and one can act as anode and the other one can act as a cathode. Okay, or in this example, there can be regions in the same material that can act. One region can act as an anode and the other region can act as a cathode, like it is happening here within the same material. So the anodic and cathodic regions has to form, and they have to be in contact, in electrical contact. The reason why, because the electrons need to be transferred from anode to cathode. In this case, because it is the same material, electrons can flow through the same material. But if you have two different materials, there has to be some electrical contact that will transform the electrons from one place to another. And there has to be a liquid environment that can serve as an electrolyte, meaning the ion carrier. In this case, you see the ions are carried, like hydrogen ions, zinc is carried. So these ions has to be carried in a liquid environment. So if these three things do not present, then you cannot experience corrosion in your part. Okay, so three things: anodes and cathodes must be present, anode and cathode must be in electrical contact, and liquid environment must serve as an electrolyte. Okay, and corrosion always happens at the anode. You see, it always happens at the anode, where metal ions leave the metal surface. At the cathode, just the electrons flow from the metal to the solution. That's it. Then the question is, how do we characterize the corrosion properties of different metals? So to determine the tendency of a metal to give up its electrons, we measure the potential difference between that metal that we are interested in and a standard electrode using a half cell. You are seeing that you have a metal which is in red color, okay, and that is attached to a standard hydrogen electrode, which is platinum immersed in a solution where there is positive hydrogen ions. Okay, so this part is your standard electrode, which you use to measure the potential of the tendency of a metal to give up its electrons. So to do that, you need to have an electrical contact between the metal and the standard electrode, which is having platinum, right? So you see the electrical contact. So what happens here is that platinum will get electrons from your metal, and those electrons then will come to the surface of the platinum, where they react with the hydrogen ions, releasing the hydrogen gas. So therefore, in the meantime, your metal is losing electron to platinum. It is therefore becoming an ion and dissolving into the solution, and your material is corroding. You see, you are losing your material here. Normally it should look like this, but you are losing it. So here the metal is the anode. Remember, the corrosion always happens at the anode, which is, we call it the negatively charged sites, because it's giving electrons. And so then we are looking at the measurement here. We read an electric potential or voltage, because the electrons are flowing through, right? We read this voltage that exists between two cell halves, and therefore we read a number, to characterize the corrosion potential of this metal. And remember, they need to be connected in a liquid where the ions will be carried. This is the electrolyte. So in this, this is the electrolyte, right? That's what we call. And then each of these are half cells, and this is how we measure the corrosion potential for different metals, just connecting it to a standard hydrogen electrode. So we do this for all types of metals and read that voltage number here and record it basically, and it will give us EMF series, meaning electromotive force series, which we will use to understand the corrosion tendencies of different metals. So what you read is with the superscript here telling us this is standard potential of a metal measured against the standard electrode, and we will use this, as I said, these data to rank different types of metals based on their voltage that we read, based on the voltage we read, based on their potential. And if the metal has relative to platinum, the potential is smaller than 0, meaning is it negative. If it's negative, the potential you are measuring, or the voltage you are measuring, if it's negative, then it is the anode. But there are cases where intentionally we can use in terms of some processing like electrodeposition. In that case, you attached a metal relative to platinum, the voltage you read is positive. Okay, that means your metal is now the cathode. The platinum is actually gonna corrode. But since platinum is what we call a noble metal, it is inert, chemically inert, the electrons therefore will come from actually the hydrogen gas. The hydrogen gas will provide the electrons to platinum, and this will the electrons will be then transferred to the metal, and those electrons will then be captured by the metal ions in the solution, and they will be reduced into the surface, becoming a neutral metal atoms basically, which is being deposited on the surface. And as you can see, the surface is growing, so you are actually depositing your metal on top of the surface of the metal itself. So you can actually do different types of metal coatings, and you can deposit different types of metals into the base metal, on top of the base metal. So this is just a processing technique that can be used to deposit a layer of a metal to another on top of another metal. So here we have the standard EMF series, meaning all these metals you see, gold, copper, tin, nickel, iron, zinc, everything you see here, they are measured against this standard electrode here, and their electrode potential is red, and they are recorded here as I told you. And then some of them are positive, some of them are negative. This is, of course, as we said, they are compared to relative to platinum. Okay, so the metal with the most positive electrode potential will always be cathode. So in this case, gold, copper, okay, they seem like they have the most positive, so they will be acting as cathode. Okay, and the difference between the electrode potentials presents the driving force for corrosion of anodic metals. So as we go up, in this table, the materials are increasingly becoming inert, more cathodic. Okay, as we move down, they tend to be more like anodes, dissolve. Okay, so it means that the sodium and potassium, they have the highest reactivities, act like cathode and anode, and dissolve into the solution, corrode. So we can give one example. For example, copper is anodic with respect to aluminum, because aluminum is here and copper is here, right? So we can say copper is we can say copper is cathodic with respect to aluminum. And if the two were in contact, if you bring in contact with copper and aluminum, then which one is gonna corrode? Of course, the aluminum is gonna corrode, okay, preferentially, because it has less electrode potential. And always remember, the more positive will act as the cathode here. So there is another example given to us here for the cadmium and nickel. So let's take a look at that. So let's locate them. Cadmium is here, nickel is here. And nickel is more cathodic compared to cadmium. So therefore, cadmium is more anodic compared to nickel. Therefore, the cadmium is going to dissolve, while the nickel can be growing by the addition of the nickel ions from the solution. As you can see, it's getting bigger here, because what happens, this is losing electrons, dissolving into the solution, so this is corroding. But this one, electrons are taken by the ions, and then from the solution, and this will turn to nickel, elemental nickel, and it will start to deposit on the surface. So it explains here, electrode potential of cadmium is lower than the nickel's standard electrode potential. That's why the cadmium corrodes. So if I give you this table, and if I give you two metals, and if I tell you, if I connect these metals, which one is gonna corrode? And you should always know the one with the smaller standard potential is gonna corrode. And this here is called galvanic couple. When you have galvanic couple, let me write. When you connect two different metals electrically in a liquid, so you see there is the electrical connection here. The electrons can be transferred. There is the electrolyte that carries the ions, and there is the anode, and there is cathode. So all these present checked to make the corrosion possible. So this is to show you, without the electrolyte, corrosion cannot happen. So even if it's a grapefruit, if you put copper in one side, insert copper, and if you insert zinc to another side, you are now providing a perfect situation for corrosion to happen. First, there is an environment that can transfer electrons, and there is an environment that can transfer ions. So zinc will the electrons will dissolve and transfer to the copper, and at the surface of the copper, the hydrogen ions are getting the electrons, and zinc is dissolving. There's the oxidation reaction, and also in the environment there are hydrogen ions. So in reality, this table of course is measured when you have metals immersed in their standard solutions, meaning they have 1 molar of each of these ions dissolved in the solution. So these are standard electrodes. But in reality, of course, this can change. Of course, this is also measured at 25 degrees C. But the temperature can be different, and we know temperature affects diffusion, and diffusion is the motion of electrons, ions, and which is going to affect corrosion. So that with temperature, the corrosion properties will change. With the concentration of the solution, the properties will change. So in this case, how are we going to measure this difference between electrode potentials? Because for standard electrodes, we know between the nickel and cadmium electrode potentials, the difference was, if you go back, 0.153 volts. Is it going to be the same if you have non-standard solutions? For example, you can have different molarities of cadmium and then nickel in the solution. So it will change, of course. So then how do we find it? And this is the equation given to us to calculate the electrode potential differences when we have non-standard solutions. So here we are using the information from EMF series, and then there is temperature T, there is F, the Faraday constant, there is X and Y. X and Y comes from the concentrations here, and N is being the number of electrons per unit of reaction. It's here 2, right? R is the gas constant. Alright, so based on this equation, if you look at how you can reduce this potential difference between cadmium and nickel, if you look at this and this equation, you can see that if you increase X and if you decrease Y and if you increase the temperature, you can reduce the potential difference between them. So even though the previous table we have learned this one, EMF series, that was generated under highly idealized conditions and has limited utility, it nevertheless indicates that the relative reactivities of metals, and a more realistic and practical ranking is provided by the galvanic series which you are seeing here, because this presents the relative reactivities of a number of metals and commercial alloys in seawater. Okay, the alloys near the top are cathodic here and unreactive, whereas those at the bottom are most anodic, like here. No voltages are provided. So the ones that says passive next to them, they are passivated, meaning they have a protective oxide layer formed on the surfaces, which slows down the corrosion rates. And we can now look at the forms of corrosion. Okay, so uniform attack. So it is a form of electrochemical corrosion that occurs uniformly over the surface. So over the entire exposed surface. So that means in microscopic sense, the oxidation and reduction reactions occur randomly over the surface, such as rusting of steel, iron, etc. This is probably the most common form of corrosion. Selective leaching is found in solid solution alloys and occurs when one element is preferentially removed as a consequence of corrosion process. The most common example is the zincification of brass, in which the zinc is selectively leached from copper zinc brass alloy. This will of course damage the mechanical properties of the material, because then only a porous mass of copper will remain who lost its zinc, and the material changes its color from yellow to red. Intergranular corrosion. So microstructural features like grain boundaries can give rise to galvanic corrosion within a single piece of metal. Grain boundaries are generally anodic with respect to the grain, hence it corrodes more rapidly. That's why, for example, if you have fine grain size, it will lead to higher corrosion rates. Galvanic corrosion is the form of corrosion we are familiar when you have two different metals that are physically joined in the presence of an electrolyte, and the metal that is more anodic will corrode. And there is stress corrosion. The name will tell you this is resulting from the combined action of an applied tensile stress and the corrosive environment. So both influences are necessary. In fact, it is possible some materials can be inert in a particular corrosive environment, but can be become susceptible to corrosion when the stress is applied. So with stress corrosion, small cracks form and then propagate in a direction perpendicular to the stress. The best way to eliminate the corrosion, stress corrosion, is to basically lower the magnitude of the stress. You can reduce this by reducing the external load, or you can increase the cross-sectional area perpendicular to the applied stress, because we know stress is force over area. Erosion corrosion arises from the combined action of chemical attack and mechanical wear as a consequence of fluid motion. Virtually all metal alloys are susceptible to erosion corrosion. So one example, it is commonly found in piping, especially at bends, elbows, where there is abrupt changes in the pipe diameter, because at these positions, the fluid changes direction or flow. Suddenly the flow can become turbulent, and those regions are susceptible to erosion corrosion, and you can see some images in your book. Pitting corrosion, it's a very dangerous type of corrosion. It is a very localized corrosion attack in which small pits or holes form. So they generally penetrate from the top of a surface downward in vertical direction. It is very dangerous because it can become undetected and it can cause failure. You see the images here. So, variations in surrounding environment can cause corrosion, such as variation in oxygen content in electrolyte produces anodic and cathodic regions along the surface. So an area low in oxygen will be anodic to areas high in oxygen content. In practice, variations in oxygen content are associated with like crevices under bolt heads and rivet heads. So that's why it is called crevice corrosion. So narrow or confined species around those regions in the electrolyte, the oxygen will be low. So this creates also galvanic corrosion. One area will be anodic, one area will be cathodic, just because the electrolyte composition is different. So what can we do then to prevent corrosion? So what you can do, the first thing you can do is you can use metals that are relatively unreactive in the corrosion environment. Another thing you can do is use metals that passivate, meaning they form a protective oxide layer on top of them. Like aluminum forms aluminum oxide, or stainless steel form chromium oxide. So think about aluminum foil you see every day. Do you ever remember seeing a corrosion in aluminum, or do you ever remember seeing an oxide film? No, this film is always forms on top of aluminum, and it's very thin. And why does it slows down the corrosion? Because remember, the corrosion is actually diffusion process. What happens here, the metal ions from the metal has to diffuse through this oxide layer to reach the electrolyte, the environment, basically, right? So for them to go through this metal oxide, they need to diffuse, and this diffusion is controlled by that oxide layer, and it is very slow. So even though this film is thin, it slows down the corrosion, and it can take actually very, very long time for species to be able to diffuse from this metal oxide film that is forming on top of like aluminum or stainless steel. So then we call these, the metals are passivated, the oxide film form and on top of them, and it prevents their corrosion. Another thing, since corrosion requires the diffusion of species like ions, and you can lower the corrosion rate by lowering the temperatures, because it will also reduce the diffusion rates, right? So if you lower the temperature, if there's a possibility for this in your application, this will also reduce the corrosion rate. Or you can apply physical barriers, some protective films and coatings. So there are inhibitors. These are substances that when added in low concentrations, it can decrease the environment's corrosiveness. So for example, it can remove oxygen gas by reacting with it. So it will slow down oxidation reduction reactions by removing the reactants, or slow oxidation reaction by attaching species to the surface. There is also cathodic or sacrificial protection, and most commonly used technique here. In this case, you can see in galvanized steel, what happens, the steel is coated with zinc. So when there is a damage to the zinc protective layer, instead of steel being corroding, the zinc will preferentially corrode. So that's why this is also called sacrificial protection, or sacrificial anodes like zinc, magnesium, because this zinc and magnesium, they become anode with respect to iron. So they are anodic with respect to iron. And when there is a galvanic cell form, there is the electrolyte, there is steel in contact with zinc. And what happens, zinc will become an anode, and it will sacrifice itself. Instead of steel is corroding, steel is going to be the cathode. That's why it's called cathodic protection. You can also do this using a sacrificial anode like magnesium, as I said, attaching to the steel pipe with a cable. So what happens, it's gonna be, instead of the steel is corroding under earth, underground, the magnesium will start to give its electrons to the solution, to the steel, and it will lose, it will form ions and dissolve into the soil. You can also understand this if you get the EMF series, compare the iron with respect to zinc and magnesium. You are seeing that zinc and magnesium, they are anodic compared to iron. That's why when you coat the surface or attach it in this form, preferentially instead of steel, the magnesium or the zinc will corrode first. But these are sacrificial, meaning the zinc will go away at certain time, or the magnesium will go away because it's dissolving into the environment. So you need to, sometimes you need to keep replacing these coatings or keep replacing these anodes, so to continue provide protection. So in summary, we have learned that corrosion involves electrochemical reactions. So there is electrons given up by metals in oxidation reaction and electrons consumed in reduction reactions. Metals and alloys, they are ranked in terms of their corrosiveness in EMF series and galvanic series. Temperature and solution composition affect corrosion rates. Forms of corrosion are classified according to their mechanism, and corrosion may be prevented and controlled by material selection, reduction of temperature, applying physical barriers, adding inhibitors, or cathodic protection.